So this is module 1. By the way, this is semester 3. It's module 1, and it's about single area OSPF version 2. So OSPF, it's a protocol, a routing protocol. It's a protocol that is used to route packets from one network to another network, mostly on a remote network, or used to LAN remote networks. So OSPF, it stands for Open Shortest Path Fast, is open shortest, then pass and fast. Yeah, not fast, but this is this fast. This. Okay, so that's it. So within this module, these are the areas that we are going to cover or go through. Open shortest, fast, pass fast, features, and then characteristics, then the packets, and then the operations. So the main objective is to explain single area OSPF operation. OSPF operates in both point to point and then broadcast multicast network. So features and then characteristics. With OSPF is a link stage routing protocol that was developed as an alternative for distance vector. It's a link stage routing protocol, and it was developed as alternative for the distance vector. So this one here, it actually bases on the capability of the link of the port, the speed of the port. But when it comes to distance vector, where we have RIP, routing information protocol, it's used to base on the distance from source to the destination. But this one here, even if the distance is long as the stage of the link is favorable, the speed is reasonable, then so instead of relying on the distance, this time with OSPF, it relies only on the speed of the port. So OSPF has significant advantages over RIP in that it offers fast convergence and scales to much larger network implementation. So OSPF is a link stage routing protocol that uses the concept of areas. So a network administrator can divide the routing domains into distinct areas that help control routing updates traffic. So this protocol, it can be used in regulating a moment. Okay, so OSPF is a link routing protocol that uses concept of areas. A network administrator can divide the routing domain into distinct areas that help control routing update traffic. That with this OSPF, it supports you can use it to divide your network or group the network into groups or into areas, and in doing that, you will have reduced, or you will actually in position to control the updates, the traffic updates. So a link is an interface on a router. So you don't need to get confused. What is a link? So a link is just an interface on a router. A network segment that connects two router, a network segment that connects two routers, or stub network such as Ethernet LAN that is connected to a single router. For a stub, it is always in form of like a headquarter and then the branches. So when it comes to a branch it can actually have other network attaching on the branch, but from the headquarter, a branch it will be treated as just a single branch, even if it has other networks on it. So information about state of information is called a link state. The information about the link, about the state of the link, it's a link state. So all link state information include the network prefix, that is the network address, then the prefix length, the subnet mask, and then the cost. The cost is the distance from the source to the destination. So this module covers basic single area OSPF implementation and then configurations. So components of OSPF, all routing protocols share similar components.
That it's
Yeah. So components of OSPF, all routing protocols share similar components. They are they all use routing protocol messages to exchange route information. So the messages help build the data structure, which are then processed, uh, uh, using routing algorithm. So routers running OSPF exchange messages to convey the routing information using 5 types of packets. And among the packets out of 5, we have what you call hello packets, database description, link state request, then link state update packets, and then link state acknowledgement package. So within hello package, it's just to test the neighbor, if the neighbor is online or not. Then the database description, they start exchanging the database to each or to the neighboring device. Then link state request, one or the router it can request information, the the state information about the state of the link. That is the request, and then of course where there is a request we expect the update, and then the link state acknowledgement. Once the device that tried to request, once it gets the update, then it acknowledges the packet. So these packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about uh, the network. These are the five different types of OSPF routing information packets. So from the time when you activate or enable OSPF, you expect to go through all those things for the device or the router to be fully converged with the other neighbors or other routers. They have to go through those 5 different types of packets. So still under components, OSPF messages are used to create and maintain 3 OSPF database. that all that information that is exchanged, it has specific areas or the location where they are stored or kept. We have what you call adjacency um, database, and adjacency database, you can call it neighbor table. We have linked state database, that is the topology table, because with topology table, it's the information about the entire topology. So it's from the topology table where the routing table is extracted from, and the routing table is derived from forwarding database. So in database, those are the links that are in forwarding state, and that is where the roots, the primary root is generated from, and then dropped into the routing table. So with neighbor table, it lists all the neighbor routers to which a router has established what we call bidirectional communication. Bidirection, it's two-way. So this table is unique for each router. So each router, it has its information concerning two, because if it's router 1, then it has to have the information on how to reach this other device. Topology, it lists information about all other routers. But in neighbor table, if router 1, for router 1, it can actually have information on router 2, maybe routers, the way they are connected to that very router 1. But the topology, it's all the information. If there are 20, if there are 30, if there are 100, each router, it has to have information about 99. That is if there are 100. Then with routing table, it lists, it's just a list or lists routes generated when an algorithm is run on the link state database. So each router's routing table is unique and contains information on how and where to send the package to other router. It can be viewed using the command, which is this. For topology table, it's show IP OSPF database. For neighbor table, it is show IP OSPF neighbor. So the router builds the topology table using the router builds the topology table using results of calculations based on the Dijkstra shortest path first algorithm. So the algorithm that is used to build the router, to build the topology table, it is so with OSPF, it has the algorithm called the Dijkstra shortest path first algorithm. It's the one that is used to build topology table. So the shortest path first algorithm, it creates a tree by pressing each router, as you can see, each router at the top of the tree, and then calculating the shortest path to reach each node. That every router, it is pressed, or it is used as the top it is pressed at the top of the tree, and then you start calculating the best path from, or the shortest path from that very router then to this other router. So whichever that comes at the shortest path, it is the one that is pressed in the topology table, and then still on top of that it becomes, or it is pressed in the routing table. So OSPF, it presses the best routes into the forwarding database, which is used to make the routing table. So link state operations. To maintain routing information, OSPF routers complete generic link state routing process to reach a state of convergence. So the following are link state routing step that are completed by the router. Establish neighbor adjacent, exchange link state advertisement, and then build link state database it executes the shortest path algorithm. So once the link state database is in place, then automatically the shortest path first it's going to use this database and then selects the shortest path first. Single area and then multi-area OSPF. So to make OSPF more efficient and scalable, OSPF supports what we call hierarchical routing using areas. So an OSPF area is a group of routers that share the same link state information in their link state database. So OSPF can be implemented in one of the following: single area OSPF, multi area. So with single, all routers are in one area. Best practice is to use area 0. The best practice to, if they're in the same area, then you can use area 0. Then when it comes to multi-area OSPF, OSPF is implemented using multiple areas in hierarchical fashion. So all areas must connect to the backbone area. So if you have to have multi-area, you can have these other areas, but all these other areas, they should connect to backbone area, which is area 0 or a single area. The focus of this module is on a single area, OSPF version 2. As you can see that all these routers, they are in a single area, and that area is area 0. So with multi-area OSPF, there are logical topology design options with multiple OSPF. So small routing tables, when it comes to multi-area, it helps in creating small routing tables, because of course you'll have groups. Instead of you having one group like this, that it is area 0. Now this time, if you have areas, you have 1, 2, you will have reduced. You will have reduced on the routing table. So the routers in area 0, they will just form their routing table, and then even in area 0 and that to reduces on that. So reduce the link state update over head. So still the same, in case let's say there is a need for broadcast messages, those broadcast messages, they will actually be populated or keep rotating within area 1. They will not cross to area 0, neither to area 2. Then reduced frequency of shortest path first calculation. You can imagine, because each router here, if there are 100 routers, then it means that each router, it has to process 99 info the state information about 99 routers. But if they are in groups, then automatically it will only the need for calculation, it will actually raise from this area 1 or maybe area 0. That is if a router it's within area 0 or in area 2. So we have the illustration or the figures you can see here. So these areas, they will be able to communicate together, but handling information, managing information, it will be done within the areas. Then we have version 3, OSPF version 3, which is for IPv6. So if you're dealing with IPv6, then you have to use OSPF version 3. It is equivalent to version 2, version 2 for exchanging IPv6 prefix. So IPv3, sorry, OSPF version 3 exchanges routing information to populate IPv6 routing table with remote prefix. Note, with OSPF version 3 address family feature, it includes support for both IPv4 and IPv6. So once you're using IPv6, you can bring in IPv4 and then IPv6 together. But if you're using only version 2, OSPF version 2, you want to bring in aspects of IPv6. So OSPF version 3, it has the same functionality as version 2, but it uses IPv6 as the network it uses IPv6 as the network layer, transport, and then communicating with OSPF version 3 peers and advertising the IPv6 route. So OSPF version 3 also uses shortest path first algorithm as the computation engine to determine the best path route the routing domain. So version 3 has separate process from its IPv4 counterpart. So the processes and then operations are basically the same as in IPv4. So OSPF packets, there is a video here that will actually demonstrate or help you to understand the hello packets, the database description packets, link state request packets, update packets, and then link state advertisement. So the table summarizes 5 different types of link state packets used by OSPF version 2. Version 3 has similar packet types. The hello that discovers neighbor and builds the adjacents between them. Then the database description checks for database synchronization. The databases between the neighbors get synchronized between the neighbors. Then link state request specific link state record to request specific link state the record. And then we have updates where there is a request, of course, we expect the updates. And still there are those updates that are generated without requests. In case, let's say, a link is down, so that router where the link is, it's not going to wait for the other router to request for information on a specific link. It can send the update. So link state acknowledgement, it's just all about acknowledging the other packet type. So where there is an update, then we expect the acknowledgement to happen. So with the OSPF package, the link, okay, the link state updates. So this is just a package. It's about the updates. Remember, I talked about saying that there are even those updates that they are sent when there is no request. So they are also used in forwarding OSPF routing updates. So the update packets can contain 11 different types of link state advertisement. So version 3 renamed several of these link state advertisement and also contains 2 additional link state advertisements. So link state updates and then advertisement are often used interchangeably, but the correct hierarchy is link state update packets contain link state advertisement message. So within the updates, we have type 1, 2, 3, 4, 5, as you can see, hello, database description request, and then within this, the update and the acknowledgement. These are different types. There are 5. So with link state updates, well, these are different, 5 of them, different types of the OSPF packets. But within these 4 link state updates, we have these several packets. So within this update, we have link state advertisement types here, 1, 2, 3, up to 8. So there's router link state advertisement, then 2, it checks for database synchronization. So we have 3, 4 summary. It's just a summary of link state advertisement. Then 5, which is autonomous system external. Autonomous system external. That is if it's from the external network, the information from these other areas in the scenarios when you use areas. Then multicast OSPF linkers. Link state advertisement, that is if the messages match in those updates, messages match to which these other multiple groups of nodes. Then we have defined for not so stable area, and then external attributes. External attributes for this on-border gateway patrol. So with OSPF, so now being this OSPF being very powerful, sensitive operating system, so not but protocol, and it is used to group the network. That's the reason why when it comes to the packets with updates, then there's information that we generate from one group, from one area then to another area. But that's the reason why with updates, there are other sub types of OSPF packets. So the hero package here, which is type 1, OSPF type 1 package. Hello packets are used to do the following: discover the neighbor, advertise the parameters on which the 2 routers must agree to become the neighbors, then elect what we call the designated router or backup designated router. Now that we have the areas and groups, it's going to be about like the leader, that anytime there is an update or there is a change in the topology, then that router that is responsible or where the change has happened, it sends an update. It sends an update onto the designated router, and then the designated router, it's the one that does the updates onto all these other routers in the same area. So OSPF operations, this is the video that will take you through all the operations. There are 7 states. We have the down state, initial, then 2-way, exchange start state, then exchange state, loading, and then full state. So if you go through your account, you will be able to play the video and you go through these states. So in down state, no hello packets are received. In other words, the status is down. Routers send hello packets. So with router, it sends the hello packets, but it's not going to receive, and then transition to initial. So in initial, the hello packets are received. So if an interface or a link it is in initial state, it can receive at the same time it can send. They contain router ID. In initial, they contain an router ID. So meaning that the router, it has to have the ID of sending router. So transition to two-way. So two-way stage. In this stage, communication between the two routers is bidirectional. That router 1 and router 2, they can send, receive. So on multicast link, the routers elect on multicast, sorry, not multicast, multi access link, the device, they will actually elect the DR and then BDR, which one should always advertise. Advertise. These other content they can update, and then the DR, it advertises. You know, this is what is happening, or this is what has happened, and then it advertises to all other. But when it comes these other routers, for them they update the DR. Oh, I'm router 1 and this is what I have as of now. Oh, this network is down. So exchange start stage, that on point-to-point network, the two routers decide which router will initiate on point-to-point, which one will initiate database description packet, which one is to send first. Then exchange stage, routers exchange database description packets. If additional router information is required, then they transition to loading. If additional route information is required, then transition to loading. Otherwise, if there is no additional information that is required, then it can skip and change to full stage. So in loading stage, link stage request, now it needs the information. Requests and link state updates are used to gain additional route information. So route are processed using shortest path first algorithm, and then after that transitions to full stage. And in full stage, the link state database of the router is fully synchronized. Establishing neighbor adjacents. To determine if there is an OSPF neighbor on the link, the router sends a raw packet that contains its router ID out of all OSPF enabled interface. So the raw package is sent to the reserved all OSPF router IP v4 multicast address that begins with 224 with this to all OSPF router. And only OSPF version 2 router will process these packets. So once the multicast is sent on this, it's only the router that will process that packet. So OSPF router ID is used by OSPF process to uniquely identify each router in the area. So the ID or the router ID is a 32-bit number formatted like IP address and assigned to uniquely identify the router among OSPF peer. So those router ID, it is formatted in format of IPv4 address, of course without subnet mask, and not assigned on an interface. So when a neighboring OSPF enabled router receives a raw packet with router ID that is not within its neighbor list, then the receiving router attempts to establish an adjacence with initiating router. Adjacence with initiating router. So this router ID, it is used to uniquely identify the router in the area So the process routers are used to establish adjacency on multi-access network. We have down to initial stage, and then two-way stage, and then elect DR, and then BDR. So when with down this, when OSPF version 2 is enabled on an interface, router 1 transitions from down to initial and starts sending the hello out of interface in an attempt to discover the neighbor. So in that process, when it is sending hello message, it is trying to discover the neighboring routers. So in initial stage, when router 2 receives hello package from the previous unknown router 1, it adds that router's one router ID to its neighbor list and then responds with a hello package containing its own router ID. That in the first place, once the router tries to communicate with the neighbor or sending a hello message to the neighbor, and then the neighbor will also, in that process of initial stage, the neighbor will try to communicate back to router 1 using router's ID. So once that ID is not known or listed in the router's information, then the router will capture that, and then they compare the router ID, the sending, and then the receiving. So if the router ID is for the sending, if we have these two routers, we expect the ID1, then ID2. So once the two sends each other the error package at the initial state, it means that router 1 is received. This router 2, this router 1. That router 1, after sending each other the error message, and then at the initial stage, router 1 can receive, and then this receive. Once it receives, then automatically it will have to compare the router ID. Is the router ID in the error package known on router 2? So if it is not known, it's going to be recorded. So still as it is recording that ID, it's going to be compared with the ID for router 2. And they see which one has the highest router ID. Of course, the one with the highest ID, router ID, it will become the DR, and then the other one with the least, it will be the DBR. So in two-way, router 1 and router 2, router 1 receives router 2 hello, and notice that the message contains an R1 router ID in the list of R2's neighbor. Then R1 adds R2 router ID to the neighbor list and then transition to two-way. So in two-way, if router 1 and R2 are connected with point-to-point, they transition to exchange start. If R1 and R2 are connected over the common Ethernet, then the DR and BDR elections occur. The process of electing DR and BDR. So where the router with the highest router ID or highest priority is elected, it is elected as DR. And then the second highest, or the one with the least. Now with second highest, it means that there are more routers. So the one with second highest, it will become the designated backup designated router. Why do we need DR and BDR? It is just to ease the communication, not actually to control the updates, to control updates. So every time there is an update, the router it's supposed to contact the DR. It sends that update to DR. So it's only DR that has that obligation of advertising the changes on a specific router to all other routers. After the two-way stage, routers transition to database synchronization states. This is a three-step process as follows. Decide the first router, which router is going to initiate, like exchange first. So the router with the highest router ID, it sends its BDR database description first. Then exchange database description as many as needed to convey the database. Now in conveying database, to make sure that all these other devices, the information, they are actually synchronized, the information are synchronized. So the other router must acknowledge each. So every time a database description is exchanged to the other router, then the other router that has received, it has to acknowledge each database description. So if it's connected maybe to 10, and then all these other 9, they have to receive, they have to send back the acknowledgement. Then sends a link stage request. So each router compares the database description information with the local, link state database. So if the database description has more current information, then the router transitions to the loading state. So after all link state requests have been exchanged and satisfied, then the routers are considered synchronized and in full state. Updates are sent when the changes are perceived or incremental updates. So every 30 minutes. So for the updates, when there is a change, that is when the updates are exchanged, or every after 30 minutes. So multi-access network can create two challenges of the OSPF regarding to the flooding of link stage advertisement as follows: creation of multiple adjacents, and then extensive flooding of link state advertisement. So multi-access network, it's not like point to point, because with point to point, it's like you having the immediate neighbor and that is it. Just point, there are two ends, this one and then two, and that is it. But with multi-access, we expect a switch, an intelligent device connecting switch routers, as you can see here. So there are multiple adjacent. And what does that mean? That you're going to have each device, it's going to have so many neighbors. And in having so many neighbors, then automatically we expect extensive flooding of link stage advertisement. That each router it has to advertise. So to sort out that problem or to mitigate that limitation, there is a need for DR. So once there is DR and BDR, and the function of BDR is, in case let's say DR fails, then the BDR it can take over. So those are the the challenges of multicast network. When OSPF is enabled on such topology. So link state advertisement flooding with the DR. So in an increase in number of routers on multi-access network also increases number of link state advertisement exchange between the router. So this flooding of link state advertisements significantly impacts the operation of OSPF. So if every router in multi-access network had to flood and acknowledge all the received link state advertisements to all other routers on the same multicast network, then the network traffic would become quite difficult, challenging, or chaotic. So on multi-access network, OSPF, it elects DR to mitigate that limitation, the DR, so that whenever there is an update, the update it is sent to DR, and then the DR is the one to send the advertisement. And now, once it sends the advertisement, the acknowledgement, it's going to be pointed, they are going to be pointed back to designated router, not these other routers. So the distribution for link stage advertisement sent and received. So we have even a BDR. The BDR are also elected in case the DR fails, then all these other routers they become. So we expect two roles, that is DR and then BDR. So if the router is not DR or neither BDR, then it's DR others. DR others. So these DRs, they are the ones that sends updates to DR, and then DR communicates to this other DR with link state advertisement. Note, DR is only used for dissemination of link state advertisement. The router will still use the best next hop router indicated in the routing table for the forwarding of all other packets. So with the advertisement, just to control advertisement, who should advertise? Is it every router? But when it comes to these other packets, they will have to use the best next hop router indicated in the routing table for this other information. But in advertisement updates, that is when we need those two roles. So that marks the end of